These are the notes on the original conservation law, the notes on conservation of energy. Remember that potential energy is different from kinetic energy. Potential energy is stored in a system, sometimes by its position. Kinetic energy is the energy of the moving object based on its mass and its velocity, as you know. So we're going to be talking about how these two interplay with each other, and we've already gotten into that a little bit ahead of time, but now we're going to see the full-on conservation law. So boom, here it is, the conservation of energy law that Leibniz was talking about. So E equals PE plus KE. That means the total energy, E, is equal to the potential energy plus the kinetic energy. So one of them might go up, but then the other one has to go down. The sum of them remains the same. There are other ways of writing this equation. For example, I could write PEI plus KEI equals PEF plus KEF. But I think this form of it is the least confusing. So what you're seeing is, oh yeah, the total energy is the sum of the two. And we'll talk in the example about how we add these and how sometimes we have to use the absolute value of them. I'll just leave that for the examples. So in any event, you have potential energy and kinetic energy. This, by the way, is sometimes referred to as the mechanical energy, and this leaves out other considerations. So you cannot really say that this law is absolute unless you include other forms of energy. And so again, it's a simplified model, but this is the one we're going to use in this class. So to understand the conservation of energy, let me take a moment to discuss gravitational potential energy. I'm representing it as PE, just potential energy. Okay, obviously, as it says here, it is measured in joules. Energy is measured in joules. The thing about gravitational potential energy is you have to pick a reference frame. It is always measured relative to a reference point. Because you could say, well, mgh, the mass of the object, Earth's gravity, and the height, okay. But the height above what? The height above 0. So where's your 0? Well, you get to pick that. And we usually pick a 0 that's just convenient. We usually pick the 0 of wherever we're starting, but you don't have to. You could make the 0 always the floor. You could make the 0 always your eye level. You have to choose that. So because of this, potential energy can, of course, be above that, positive, let's say higher than the reference level, or it could be lower, it could be negative. So there is no absolute potential energy. Imagine if you're standing on a trapdoor. You could measure the potential energy relative to that trapdoor, right, above that. But then what if you open that trapdoor? Now there's a new floor. You could measure from the floor below that. What if there's a trapdoor on that floor? You could keep losing the floor below you and measuring it from a lower point. What if the Earth magically disappeared? What would you be measuring the potential energy above? The sun, the surface of the sun? What if the sun was gone, the center of the galaxy? You know, so potential energy is always going to be measured relative to your reference frame. And actually, so is kinetic energy. Kinetic energy, you've got to pick like a reference point that you consider not moving. So usually that's the observer, that's you. So just remember that this is always measured in reference to something else. So oftentimes we pick the floor or the ground to measure above, but you don't have to. You can measure from any point you choose. And it's always great to have a number drop away to 0, isn't it? So you probably want to pick where you're starting. Most often we pick wherever we're starting as 0. So that's something to remember about potential energy. One way to talk about potential energy is to talk about a novice juggler. Let's say this guy just learning how to juggle, not very good. So all he can do at this point is throw an orange up and have the orange fall back down into his hand. Let's ignore the sort of side-to-side motion. Let's just talk about it going straight up and straight down. Well, if you're going to talk about the potential energy and the kinetic energy of this orange, well, you got to choose a reference frame. So probably an easy point to choose would be the juggler's hand, because the orange is thrown from that point, and you could measure the height above that, right? And then it's going to fall back down into his hand. Let's say he doesn't move his hand very much, he just throws it. So it's at the same level when he catches it as well. So we're going to be using this to discuss the interchange of potential energy and kinetic energy. Okay, so the bad juggler. So let's consider the system of an orange used by a juggler and the Earth. The energy in the system exists in two different forms: the kinetic energy of the orange when it's moving, and the gravitational potential energy of the orange based on its position. If the juggler throws up an orange from his hand, well, initially, if we consider the reference frame his hand, the orange has only kinetic energy moving upward. But as you know, an orange thrown upward won't go forever. It'll eventually stop. When that orange stops at its highest point, that is when its potential energy is the greatest. Okay, it is a certain height above his hand, mgh. So that amount of energy that was initially imparted to the orange has now been converted from kinetic energy into potential energy. But as you know, the orange will come back down, returning to his hand level, and as it does that, the potential energy is converted back to kinetic energy until his hand stops the orange. So you can think of this as an interchange between kinetic and potential energy. So on the way back down, potential energy changes back to kinetic energy, but at any given point, the sum of the kinetic energy and the potential energy is always a constant. So one goes down while the other goes up, one goes up while the other goes down, but if you add them together, it always equals the same number. Okay, now this is of course leaving out a few factors. This is leaving out the heat that it's generating, because when an orange moves through the air, it doesn't generate a whole lot of heat, doesn't warm up the room much, but actually, if you look very, very closely at the air molecules that it's shoving out of the way, it is in fact heating them up, just very slightly. Well, of course, we like to ignore that stuff, but just so you realize that it is going on. Also, there's another way that the orange is losing energy. It's losing it due to something called black body radiation. Black body radiation is when an object basically releases infrared radiation usually and winds up at a lower temperature. Okay, but generally we aren't even talking about the temperature of the orange, so that is a very small factor. Of course, the temperature of the orange will also be heating up air molecules. And if you think about air molecules moving, well, don't they have kinetic energy? A very, very tiny amount. Every molecule that is moving has kinetic energy. So really, if you think about the dissipation of heat, some of that can be thought of as just kinetic energy, just way, way down on a microscopic kind of Ant-Man level. Okay? So the sum of kinetic and potential energy on a mechanical level, if we leave out the heat, is going to be a constant. So why did we pick the reference frame of the juggler's hand? Just because it's easy. Now we could have picked the floor, but then we would have been adding in the distance from the floor up to his hand every time. So notice that picking his hand as a reference frame is way, way simpler than picking the floor or any other point. But we didn't have to pick his hand. We just arbitrarily chose a reference level. So you can pick whatever reference you want, whatever makes you happy, whatever floats your proverbial boat. What if we were to choose the reference level, instead of being the juggler's hand, what if we just decided to choose the highest point that the orange reached? Well, then the interesting thing about that is that the potential energy, when it's at a maximum, would be 0. So at any other moment, the potential energy would have been negative. But as you know, negative and positive numbers can add together equaling 0. Interesting. So in this situation, look at the little graphs on the bottom. The kinetic energy starts out positive, the potential energy starts out negative. Then, as we approach the highest point of the orange, they both drop to zero. Well, one of them drops to zero, one of them rises to zero, if you want to say that. It goes from being negative up to zero. And then, of course, it goes back to the way it started as the orange falls back to his hand. So the reason we don't normally do this is because it's kind of confusing for the human mind. The human mind just has difficulty with negative numbers. It is inherently confusing. Now, I'm sure if you're really good at math, you can handle it, but why not make things as easy as possible conceptually to understand the concept? And we could even choose the middle ground. We could choose when the orange is halfway up as zero. We could choose anything as zero, but why do that? That's just introducing unnecessary extra calculations that we have to throw in here. So generally speaking, this is not the way to go, depending on what you're looking at, of course. Generally speaking, you probably want to set zero at wherever the object is starting or where it's ending, something like that. So notice, depending on how we define our reference frame, then the total amount of energy that we get is actually different. That's because there is no absolute potential energy or kinetic energy. It's always compared to your reference frame. So if your reference frame is the juggler's hand level, where the orange is thrown from and where it winds up, then all of your energies are always going to be positive. And they're going to add up to the total, okay, which is going to be a positive number. The lowest they will get is going to be zero. The kinetic energy will be zero when it's at its highest point. The potential energy will be zero when it's at the juggler's hand level, right? But if we choose the highest point the orange reaches as our zero, well then some numbers will be negative, right? Initially, the potential energy is negative. It only reaches a maximum of zero, and then it goes back to being negative after that point in the middle. The kinetic energy, however, will be positive the entire time, and at its lowest point, it will be zero. Interesting, right? So it's really funny that there is no absolute potential energy. You have to choose your reference frame and measure it from that. And there is no absolute kinetic energy either. It's got to be measured relative to our reference frame, which you would establish as, let's say, not moving as your reference frame of zero, probably yourself, the observer. So the law of conservation of energy states that in a closed system, energy can neither be created nor destroyed. So energy is conserved. That's why it's a conservation law. Under these conditions, energy changes from one form to another, like from kinetic to potential, but the total energy of the system remains a constant. So the conservation of energy, another conservation law, you could sort of say this is the big one, okay, in physics. The conservation of energy, energy is not created and it is not destroyed. Energy can be transferred and transformed into different forms, however. So there's a lot of different forms of energy. And we are primarily dealing with kinetic energy and potential energy. So again, the conservation of energy law can be written this way as long as we're talking about a particular form of energy, only if we're limiting ourselves. The forms of energy that we are limiting ourselves to are, again, the mechanical forms of energy, potential energy and kinetic energy, okay? Sort of like, let's say, the physical forms of energy, if you want to think of it that way. Now, it turns out, remember how we defined work as the change in kinetic energy? So if you change kinetic energy, but you're conserving the total energy, well, then you must be building up potential energy. So one way to think about work is taking away kinetic energy and turning it into potential energy, or the other way around, releasing the potential energy to turn it into kinetic energy. That's one way of thinking about work, another way to think about it. So physicists love to use spheres, right? Like spherical cows, right? So if you consider a ball, a sphere, near the surface of the Earth, Well, the sum of its gravitational potential energy and its kinetic energy is going to be constant. That means that if you move it to a different height, which of course will change its potential energy, then you must be changing its kinetic energy as well. Okay? So the total amount of energy will stay the same, but you can convert one to the other. And one way to observe that is changing velocities or changing height. Now, it might not seem that energy is always conserved, but that's because sometimes energy is turned into a non-mechanical form or into a microscopic form, like, let's say, the motion of air molecules. Energy can be dissipated when you move through the air. Obviously, you're moving air molecules, and little by little, that's taking away some of your energy, turning it into the energy of the motion of the air molecules. So it's still there somewhere. You just can't always observe it. So whenever you observe energy leaving a system, well, it might be going outside of that system, but it's still conserved in the larger universe. In one form or another, energy really is conserved. So the problem is that we have a lot of situations where energy leaves a system. It depends on how large you define your system. Is the system just the object and the Earth, as we often do, or is the system every object on the surface of the Earth, including the atmosphere? Well, it depends on how big your system gets. But if you include all the energy everywhere, it is conserved. That is something that you can say. So roller coasters are often used to describe mechanical energy in physics, and they're a pretty good example. Because you do all of that work hoisting the roller coaster up on top of that first hill, the artificial hill, right? And then that potential energy that you've established through all of that hard work is converted into kinetic energy, right? And then, of course, the roller coaster can just transfer it back and forth between kinetic and potential to get over subsequent hills, as long as the subsequent hills are shorter. What if the roller coaster came to a hill that was larger than its initial artificial hill where it was hoisted to? Well, it wouldn't make it over it. That would be a bad situation. Then your roller coaster would stop and roll backwards. So that's something they try to avoid when they design roller coasters, I guess, except the Mummy, but that doesn't really stop on an uphill. They usually avoid going backwards. People don't often enjoy that. All right, so think of a roller coaster as a great example. Picture that roller coaster as being lifted up, hoisted up onto its first point. Generally, that's going to be the highest point the roller coaster encounters. And then other than energy lost to heat, okay, due to the friction with the track, then that amount of energy is going to be conserved through the rest of the trip until they put on the brakes at the end, jarring you to a halt, right? So as long as the subsequent hills are shorter, then it should have enough energy to make it over them, right? It's converted to kinetic. That's why the roller coaster is going so fast at the bottom. And then it's converted back to potential as you go back up the next hill. But some of it is still kinetic. You keep on moving, right? You don't stop at the next hill. And so that's how roller coasters work. And it's a great way to think about the conservation of energy. Another common example is skiing, because a ski lift will take the skier up to a high point where they have a lot of potential energy, and then the skier can use that potential energy, converting it into kinetic energy to go down the hill. So that's a pretty clear example of converting potential energy into kinetic energy again. But the best way to understand this conversion between kinetic and potential energy and the conservation of energy is looking at some examples. So I'm going to show you a few examples, and I hope this all makes sense. Okay, so here is a conservation of energy problem. If a 25.0 kilogram box is dropped from the top of a 200-meter building, okay, what is the velocity when it hits the street below? Okay, so this is interesting because we've got a box being dropped from the top of a building, starting out like this, not moving, 200 meters above the street, being dropped, And what's its final velocity when it hits the street? What's its velocity? How can we tell that when initially it only has potential energy? And potential energy does not have velocity in it, does it? Interesting. Okay, now we need to define our frame of reference here. Do you know what an easy one to use is? Zero? What are you going to use as zero in this problem? I would say the street, the bottom. Okay, it kind of defines it for you because it says 200-meter building. Okay, so that's a positive number, so we're assuming that the building is in a positive direction. Now we run into a little bit of a problem with our positive and negative numbers here, okay, that you're going to see because we're going to use this conservation of mechanical energy, okay, law. And if we leave out loss to heat, this is pretty much going to be true. But there's one thing I've got to mention here that I've been playing a little fast and loose with up until now. And that is kinetic energy cannot really be negative. Why not? Because mass is always positive, right? Well, but then you say, well, can't velocity be positive or negative? Yes, because velocity is a vector, can be positive or negative, but not when you square it. So when you square a negative, it becomes positive. Therefore, no matter which sort of, let's say, direction the object is moving, the kinetic energy will be a positive number. So really, to use this equation properly, we should probably use the absolute value of the potential energy. I could have written absolute value signs here. So the potential energy actually can be negative because we're measuring it compared to a reference point. But the kinetic energy, because of its definition, cannot. Okay, so now that we've gotten that out of the way, you can really do the calculations using negative kinetic energy. It's just you have to take into account that when you take the square root, it could be a problem. You would get imaginary numbers sometimes. Okay, so obviously we're going to have to start out with the one we can calculate. What do we have enough information to calculate? We have enough information to start with the potential energy, the gravitational potential energy. Okay, and then we'll use that, we'll go from there. So let's call this potential energy initial. That's our initial potential energy. And that is going to be equal to, well, mgh. What is my m? What's the mass of the box? 25.0 kilograms. What is my g? Well, g is 9.80 meters per second squared. It's an acceleration. And normally we'd put in the negative sign, but as I just said, we're going to have to take the absolute value of this anyway. So let's just leave out that negative sign and we won't have to worry about that. Okay? Now that might seem funny, but it's just because of the way kinetic energy is defined. To use this law, you sometimes have to do, let's say, like the absolute value. You guys still learn absolute values, right? Okay, of the potential energy. And then what's the height of the building? We're going to have that as 200 meters, 200-meter building. So let's just number crunch that, multiply them all together. So 25 times 9.8 times 200 equals, and let's write out 49,000. And potential energy, it's an energy, so you probably know what the unit will be. Kilogram meters per second squared, times meters, kilograms meters squared per second squared. That's a joule. Remember, energy is given in joules. Okay, so if that's my initial potential energy, then we could talk about the overall energy. Let's say it this way. So the overall energy is going to be equal to, okay, let me get this one out, the potential energy plus the kinetic energy. So this is potential energy right here. So let me write this in, 49,000 joules. But remember, kinetic energy depends on velocity. So if I've got a box right here, it has no velocity. So if it has no velocity, then it has no kinetic energy. So the kinetic energy will be 0 plus 0. So in fact, the potential, and I'll put joules. I'll give it a unit, 0.0 joules. So the energy of the system is the potential energy when you were starting. Then of course, then you release it and it is converted. Some of it is converted into kinetic, more and more until it reaches the street. Okay, so then I could also write that the total energy is just equal to 49,000 joules. Now I could put this in scientific notation now, but let's not bother. Let's just do that at the end for our final answer. Okay. Then when it gets to the street level, when it hits the street, it's the exact opposite of this. Okay. I'm still using this equation, by the way. Okay. So when it gets to the street, then the potential energy will be 0 joules. Well, then what must the kinetic energy be? If energy is equal to 49,000, and if the potential is 0, well, then the kinetic energy has to be the 49,000 joules. Now, you don't actually have to write out these steps. I'm just showing you that it's based on this. So that's the potential energy, 49,000 joules, when the kinetic energy is 0. So that means that the total energy is just 49,000 joules, right? And then here it's the opposite way around. Notice this is switched. Okay? Now the potential energy when it hits the ground is 0 because we're defining that. We're defining the ground as 0, okay? And then the kinetic energy will be 49,000 joules. Okay? So now I can tell you that the kinetic energy that it ends with, KEF, is equal to 49,000 joules, or 4.90 times 10 to the 4th joules, if you did put it in scientific notation. Okay, so now we know the kinetic energy when it hits the street. So how are we going to figure out the velocity? What it's asking for is the velocity. Well, let's go back to this equation. Okay. By the way, even though we don't have a positive or negative sign here, we're kind of using absolute values. We know which direction it's going, don't we? It's going down toward the street. Okay, so even without that, we can still tell the direction. Okay, if you want to indicate that, you could write downward or something like that. Okay? So if that's my kinetic energy, I'm going to put that right there. I'm going to write 49,000 joules. I don't know why thousands are so impressive to me right now. I guess it's not really that big of a number. Times 1/2, of course. And then we've got the m again. Oh yeah, the m, it's the same m. Goes in, comes out, 25.0 kilograms. And then the v squared. Well, we don't know the v. And don't forget that it is squared. Au contraire, vélocité squared. I don't know how they say squared in French. So that's Émilie de Châtelet. She was a big advocate of Leibniz's understanding that the kinetic energy was 1/2 mv squared, whereas there was a debate about that, where Isaac Newton didn't think it was squared. So it's actually one of the few times Isaac Newton turned out not to win the argument, let's just say. He didn't win that argument. But usually he did. I mean, brilliant man. Don't want to put any shade on Isaac Newton. Is that what you say these days? I'm not up on the lingo, guys. Okay, so then we got to multiply. Well, what's 1/2 of 25? Well, obviously that's 12.5, correct? So 25 times 0.5 equals 12.5. So let me write that here. 12.5, still kilograms, because this doesn't have a unit. This is a unitless ratio. And I'll just put it into parentheses so I can still write the v squared. I'm trying to avoid running out of paper here. I'm afraid I'm going to run out of paper here. Okay? This seems to always happen. I seem to start off writing too big, running out of room. Okay. So then, of course, that is still equal to the 49,000 joules. And then what I'm going to do is I'm going to divide both sides by 12.5 kilograms, because we've got to get our little variable. We've got to isolate our variable. We've got to get it alone. And the first thing we have to do is get rid of this. So I'll just write it here. 12.5 kg divided by 12.5 kg. I guess this actually goes under both of them. Okay. And then, of course, the number cancels, the unit cancels here. And then what are we going to wind up with here? I think I have enough room. I can't really slide this much. Okay, I think I can fit it. You should be able to see it there. When I divide 49,000 divided by 12.5, 12.5 should go into that. Should be about 4,000 times, something like that. 3,920. That seems good. That seems about right. And I'm going to write that in green here. So it's 3,920. Okay, and what's the unit here? Well, a joule is a kilogram meters squared per second squared. Oh, and we're dividing by kilograms. So the kilogram is gone. It's canceled. So we've got a meter squared per second squared is what we're left with. And that, of course, equals v squared. So now we have to take the square root. Okay, the square root. So now notice if you had done it the other way, if you would put a negative in here, that would have carried through, and this would have been a negative number. But then we'd have to take the square root of it, and we get an I, an imaginary number. So we wanted to avoid that. Okay, so if we take the square root of both sides, okay, I use the most radical function according to the Teenage Mutant Ninja Turtles, radical function, and I get v equals 62.61. That rounds to 6.1, and then the units would be the square root of the units too, so meters per second. Okay. Now I want to put that in scientific notation. I don't think you'll be able to see down here, so I'll have to write it over here somewhere. I'll just write it, where can I fit it? Maybe right here, okay? So maybe I'll put in a little circle that I can write it in. Okay, so then this goes up to here. So 6.26 times what? 10 to the, moves over once, first power. Now that would be 100% completely wrong, 100% completely wrong. Okay, and obviously this is what v is equal to, if I didn't put the unit, meters per second. And if you want to describe which direction it's going, you could write downward, I guess, okay? Because because of the way we did it, we didn't get the negative or positive because of the definition of kinetic energy. But if you're just logical, you can figure out the direction things are going, okay? So again, that's just because of the squaring function. It has problems with negatives. Lots of people have problems with negatives. I have problems with negatives. You probably have problems. Most people have difficulty handling negative numbers. It messes you up all the time. Okay, so if it helps, think about this conservation of energy law based on sort of the absolute value of the potential energy and the kinetic energy. Okay, they add up to the same number. Okay, in this case, it was 49,000 joules. All right, so that is how you solve a conservation of energy problem. So speaking of jugglers, remember the juggler tosses up a ball. We just talked about that. So this one involves a juggler. A juggler tosses a 500-gram ball upward with a velocity of 3.0 meters per second. At what height above his hand are the gravitational potential energy and the kinetic energy of the ball equal to each other? What is the velocity of the ball at that point? Ooh, interesting. This is a fun one, and this one gets you to really think. So first of all, what are we going to have to do here? We're going to have to figure out what the initial energy of that ball is, what the initial total energy. But of course, when he throws the ball from his hand, his initial potential energy will be zero. It'll all be kinetic. So remember that these are going to add up to the same thing the whole time, okay? But we can easily calculate it when one of them is zero. So why don't we just do that? So let's see, let's calculate the initial kinetic energy is what we want to start with. Okay, so kinetic energy initial. By the way, I'm using cardboard because I was running low on the paper, and this is the cardboard, the box that it came in. Okay, kinetic energy initial is equal to 1/2, of course, 1/2, and the mass of the object, the mass of the object is 500 grams. So if it's 500 grams, we don't want to put grams into here, as you know, because of the definition of the joule and the newton, okay, and even the watt. We got to use another, we have to use kilograms. So we have to multiply it times 1 kilogram is 1,000 grams. And so it's like dividing by 1,000, and you probably knew to do that. And it moves the decimal over 1, 2, 3 places. So, we're dividing by 500 divided by 1,000 equals 0.5, right? So it'd be 0.5, I'll put 0.50 kg. That is our mass. So we want to put that here, 0.50 kilograms. There's a little bumpy surface here. And then we got the velocity squared, okay? So we got to put in, okay, 3.0 meters per second. And then, of course, don't forget to square it. Well, that's easy. 3 squared, one of those very famous squares, is going to be 9.0. These are both squared, right? Meters squared per second squared. And that's going to be multiplied by 0.5 times, well, this is also 0.5. Isn't that funny? So it's like 0.5 squared. Isn't that funny? So why don't we do it that way? Let's do 0.5 times, well, 1/2, of course, is 0.5. So 0.5 times 0.5 equals 0.25. Isn't it funny when you square numbers that are less than 1, they get smaller, right? And of course, that keeps the unit. It doesn't square the unit because this is unitless. This is a unitless ratio. So if the kinetic energy initial equals this, well, it's 1/4 of 9, okay? So 9 times 0.25 equals 2.25, okay? So the kinetic energy initial equals 2.25. What are the units? What are the units? Joules, right? So what we want to know is at what point are they going to be equal to each other? Well, if that is the total energy, and if the total energy is equal to the potential and the kinetic, when are they going to both be equal? When the kinetic energy is, let's say, halfway to 0, right? Because it's starting off with complete kinetic energy, and it's ending up with completely potential energy. But it's got to be like exactly in between if we divide this by 2. So why don't we just divide this by 2? And so the energy, for example, right now we've got the overall energy is the potential energy. This is 0, and then this is our total. Okay. But we could also write it as energy equals let's divide this by 2, divided by 2. So I might have to keep things to the thousandths place to make this work. It's 1.125 joules, that would be the potential energy, and 1.125 joules, that would be the kinetic energy. I'll just write that below it so you can see. So the kinetic energy and the potential energy, wouldn't they be equal? So this is kind of easier than, there's other ways to solve for this, but it's kind of obvious if you think about if they're going back and forth, swapping potential for kinetic, when are they going to be equal? Well, when it's 50-50, when it's half and half. So that's why I just divided by 2 there, okay? Otherwise, this problem is much harder if you don't realize that. It could take a lot longer to solve this. So now it's wondering at what height, the real answer we're looking for is the height at which these are equal. And what is the velocity when they're equal? Interesting. So I want to do these ones on a separate block of cardboard so I can maybe slide it up if we get near the bottom. So at what height above his hand are the gravitational potential energy and kinetic energy equal? So let's do the height part first. To get the height, we have to extract it from this equation. Potential energy equals mgh, right? Equals mg h. And what we're solving for is the h. Okay? So this would obviously be in between when he throws it and when it reaches its highest point. That's when the potential energy would be all the energy. But here it would be half the energy, right? So let me put that in place of the PE. 1.125 joules would equal, and don't we know the mass? We already did the mass, remember? The mass, we already converted it. It would be 0.50 kilograms, right? And then what's gravity? Well, remember that gravity is actually going in the other direction that the ball is going, but honestly, because of the way we're writing this, I'm going to have to just put gravity in as positive here. Otherwise, we'll wind up with a negative height, which is not what we really want to know. So I'm just going to put it in as 9.80 meters per second squared. Otherwise, we'd have a negative height, which we do not want. Okay, it would kind of mix. If you did the problem and got a negative, you'd realize that Well, it's got to be above his hand. Okay, so it's measuring in this direction. So in this case, I'm just going to put in the gravity as positive. So then let's multiply these together. Well, 0.5 times 9.8, well, we know that one, right? That's 4.9. That's occurred previously. And so let me write this again. 1.125 joules equals, let's multiply these together. 0.5 times 9.8 and equals 4.9. Okay, 4.90, let's write it. So we've got 4.90, and then kilograms times meters per second squared, kilogram meters per second squared, right? And then times h. Okay, so this is pretty easy. All we have to do to solve for h is to divide both sides. Let me just divide both sides by 4.90 kilogram meters per second squared. Divide it over here, same exact thing. Remember, you always have to be equitable to equations. You have to do the same thing to both sides of your equation. So the term cancels, the units cancel, and we'll just have h. I knew I was going to run out of room here. I can slide this up a bit. Okay, and then over here, what do we get? Okay, 1.125 divided by 4.9 equals, this is a small number. This is not a big height. 0.2, and then it's 295. So I'm going to round it to 30, because we do want to keep that digit here. And then what's going to happen with my units here? Well, joules are kilogram meters squared per second squared. I'm dividing by kilogram meters per second squared. So everything's going to cancel out of that joule except for one of the meters, which is exactly what we want because height had better be in meters. Now let's write this in scientific notation. H equals, I'm going to write it the opposite way, 2.30. Now you can see why I kept that digit, okay, for scientific notation purposes, times 10 to the, well, let's see, now we're moving that way. We're moving that away. So what does that do to your exponent? It makes it negative, and we moved it once, -1. So remember that if your exponent is negative, that doesn't mean your number is negative. That means your value is less than the number 1. And then it doesn't mean anything without the unit. You gotta have the unit. Write your units. Write your units. Okay, and then I'm gonna circle my answer. Okay, there's my final answer. And then we're gonna calculate the velocity. So now let's do the velocity of the ball at that point. I'm gonna do the kinetic energy one on this board. Okay, so what is the velocity when they are equal? Well, if the kinetic energy equals 1/2 mv squared, right? And if we know the kinetic energy, if it is this, half of the total, then it is 1.125 joules equals 1/2. And don't we know the mass of the object? Oh yeah, we already converted that to kilograms. So 0.50 kilograms. And then we need to know the velocity. That's what we're solving for. But of course, this is velocity squared. Okay, so it's 1/2 of 0.5. That's of course a quarter, 0.25. Okay. And so let me rewrite this again with 1.125 joules. And then equals, and what is 0.5 times 0.5 equals 0.25. So it's like squaring. It's kind of like what we did here, okay? In fact, it's the exact same thing we did here because it's still the same m and it's still the same 1/2. But the v will be different, of course, because it wouldn't equal this, okay, with a different velocity. So v squared. So then if we want to get this on its own, I'll just use the red for this. We'll divide both sides by 0.25 kilograms, 0.25 kilograms. And then of course, over here, the number cancels, the unit cancels. Over here, now be careful because when you're dividing 1.125 divided by 0.25, it's like multiplying by 4. So it's going to be like 4.025 4 something, okay, 0.25 equals 4.5, okay? So 4.5 on this side, 4.50, and joules divided by kilograms? So remember, a joule is a kilogram meter squared per second squared. So the kilogram part is going to cancel, and you'll have meters squared per second squared. And that, of course, equals v squared. Well, that makes sense, because those are the units of velocity squared. So then if we take the square root of both sides, what's the square root of 4.5? Square root, this radical function, 2.12 meters per second equals v. Okay, so I hope this still fits in the camera. Let me slide it up slightly. Okay. So let's put that into scientific notation. I'll write it the other way. V equals 2.12. Now remember, we're not moving the decimal at all, so that's when you have the 10 to the 0. And then the units have to be there if you're going to have the right answer. And then let's just circle that. So when the potential energy and the kinetic energy are equal is when the velocity is at 2.12 times 10 to the 0 meters per second. Remember, it starts out at 3.0 times 10 to the 0 meters per second. Okay, so that's when the potential energy and the kinetic energy are equal. Okay, and also at the height that we had earlier. Okay, so that's how you do a calculation about when kinetic energy and potential energy are, in fact, equal. Okay, interesting, right? Good one. So that is the end of the notes on conservation of energy, one of the overriding laws of physics. Boom.